Thanks. It's a pleasure to be here. I'm going to be using these little whiteboarding things. So some of you might want to come forward. I'm going to try to encourage that by writing really small and illegibly. Okay? So, so if you want to come forward, I encourage that. Except for people who are already in the front row.
They can sit on the floor.
Yeah. Okay. So let's see. I want to talk about a crisis of faith that I had that Gromov brought on a little over 20 years ago. And basically, Gromov's point was that there were all sorts of things that were discovered in topology during the 20th century, some really good, amazing theorems. And his point was that people might understand the proofs, but they don't understand the theorems. Okay? And so let me give two examples to sort of show what this subject looks like. Okay? So here's a theorem of Shmuel. Okay? And it goes like this. Okay, here I have the n ball, and I'll assume n is at least 6. Okay, so this is, I'll say the unit n ball, but obviously it doesn't really matter. We're topologists here. Okay, and then inside of here I have something that I'm calling Sn minus 1, but maybe that's a mistake. Maybe I should call it sigma n minus 1. Okay, it's something that happens to be a sphere, right? It's a smoothly embedded codimension 1 submanifold that happens to be the n minus 1 sphere. Okay? And the theorem of Shmuel is that sigma is part of a family, sigma t, which also includes the boundary of the ball. Okay? You probably know this in more conventional terms as that if you have this, you can isotope it to the boundary. If you have a codimension 1 sphere in a ball, you can isotope it to the boundary. Okay? And this is a really good theorem. This is around the level of the Poincare conjecture. Okay? And it's the same paper. The point is that the region in between here this region in between is topological. It's even smoothly an annulus in this high dimension. Okay? So his theorem was that, that there's sort of no knot theory in codimension 1, at least in this, with this kind of interpretation of what you might mean by knot theory. Okay? That's saying that. Okay? So anyway, so that's a theorem, and I think we all understand what the statement is. Right? Okay? Here's another theorem. And this one is due to Rene Tom. And it asks the following question. Here I have a manifold, Mn. Okay? This theorem doesn't have any hypotheses on dimension. And it wants to know, does there exist, so this is, let's say that it's compact and smooth. Okay, I'm not going to do anything non-smooth today. It's a Sunday. Okay, so, okay. And the thing that Tom was interested in is does there exist some W such that the boundary of W is equal to M? Right? So this is called cobordism theory, but when Tom did it, it was probably called the cobordism problem, right? And here is his answer. His answer was extremely fruitful for future developments, which was this. He said, well, you consider the tangent bundle of M. So this is a map into the Grassmannian of n planes. N planes in R. I'll call it infinity, but infinity is just a big number. Okay? So I have my manifold. I guess we'll imagine it embedded in Euclidean space. So then the tangent bundle really is a bunch of tangent planes at every point. Okay, so then at each point you have a tangent plane. So that's a function on the manifold. It's a map from the manifold into this Grassmannian, into the space of all planes. Okay, and this is the necessary condition is that if I think about the push forward of the fundamental class in the homology of the Grassmannian, okay, this had better be 0. Okay, so the point is you look at the manifold, you push it into the Grassmannian, so there it's a chain, right? I mean, you know, that's what chains are, at least a lot of the time. And now if the manifold bounded, well, then that chain would be a boundary. So this looks pretty obviously like a necessary condition. Now, if you're a complainer, and I know that in any audience this size, there are a lot of you, right? You might say, oh, but the manifold is 1 dimension higher, so the tangent spaces aren't the same dimension, and that I have to worry about Grassmannians of n planes versus n plus 1. Okay? And then I would tell you, okay, study the homology of Grassmannians and their stability properties, and it all works anyway, even if you complain. Okay? That's not the hard part of the theorem. The hard part of the theorem is, well, I mean, this is kind of amazing, right? I mean, you look at the thing. Firstly, that chain is better than a chain. It's like typically a smooth submanifold. Generically, it'll be 1. So, and, you know, I mean, it's bounding better than just, you know, better than bounding a chain, right? The whole thing, I mean, it's just way more beautiful. And, you know, the inversion of this process is very, very highly non-trivial. And in fact, the smooth analog, the oriented analog, is also true. And that's, I don't remember, I think that maybe Milner, Novikov, Wall, and that took a good extra 10 years to do, right? So if M were an oriented manifold, right, you could do the same thing. Oh, so I didn't tell you, if M is not oriented, then I would have to look at the mod 2 homology of the Grassmannian. Okay, but if it's oriented, then I would have an integral class, and I could, again, phrase the same condition. It still would be as obviously necessary as it was in the unoriented case. Okay, and it's also sufficient, and that's actually that's a rather harder theorem. You know, about an extra decade of work by a lot of people. Okay, so these are 2 theorems, and these theorems were proved in the 1950s and 60s. And what Gromov pointed out in the 1990s at some talk at Princeton was that we just don't, you know, that we don't really understand these theorems. Okay, so what does it mean to understand this? So what Gromov had suggested was asking the following question, which is, how complicated are the objects that we need to construct? Okay, right? Both of these theorems assert that something or other exists. Right? In this case, it's saying that some isotopy exists. Right? In that case, it's saying that some null cobordism exists. Right? That if some obvious condition holds, then there exists a manifold. The question is, how insanely complicated do these things have to be, or are they really easy? That the hard, like, so there are theorems like, Dürr Fermat, right? That if you have a prime and it's 1 mod 4, then it's a sum of squares, right? And that's proven by an existence proof. And, I mean, there I think the cool part of the theorem is the theorem. Okay, yeah, you know that you can do it if and only if you're 1 mod 4, you know you're going to succeed. But what the process for finding the object is pretty easy. You just try the numbers less than the square root of p, and you do p minus a squared and see if it's a p squared or not, right? I mean, we know what's involved in implementing the theorem. In these cases, something or other exists, and we don't have a clue at all about how complicated the objects are. Okay? So what I want to do is I want to explain to you that these 2 problems really are very, very different from each other, and begin telling you about some advances that we have, but then I'll complain. I'm not going to end up on a happy note. Okay? Don't worry about it. Nothing good comes out of a midlife crisis. Okay. So Okay, so let me so here's sort of, let me tell you the situation for Smale's problem, and this spurred on a lot of work around the turn of this century. So I'm not going to say anything new about this. So the first definition let me give is what I mean by the complexity of sigma. Okay, so let's run the picture again. Here I have some sigma inside of the ball. Okay, so this will be read the complexity of sigma. Okay, and here's how it goes. I look at the soup of epsilon such that the epsilon tubular neighborhood is embedded. That's not a set. Okay. Should put the soup out there. Okay? Okay? So okay, here I have sigma, okay, and I begin drawing normals. Right? I mean, inner and outer, I'll draw both of them. But, you know, the tubular neighborhood theorem says that for epsilon really small, these normals don't intersect each other, you know, unless they were the same normal at the same point, right? That for a while, going in the normal direction is one-to-one, and that in fact you hit the whole neighborhood. Okay, right? That's the tubular neighborhood theorem. But of course, there will be a time when they stop being embedded, right? Because otherwise Euclidean space would be sigma cross R, which it isn't. Okay, so there is this epsilon, there's this last moment where it's, you know, where it's embedded. Well, right, there's this first moment when it's not embedded, more precisely, okay? And then I could look at 1 over that. Okay? Because the idea is that this isn't as complicated as this. Okay? And if you think about it, there are sort of 2 reasons why something is complicated in this view. Right? One is because somehow of the curvature of the hypersurface, right? That if you have if your second fundamental form, you know, has some, you know, some little eigenvalue, right? That'll cause you some kind of local collision of them. But it could also be that things are quite flat and far apart, but they get close to each other. Okay, either one of those would have caused this soup to be small, and then I take 1 over it because my notion of complexity is I usually like the bigger number to be more complex. This is just like, it's not a mathematical point, it's a linguistic point, which somehow matters a lot. Okay, so now we know what we mean by the complexity of an embedding, right? So what is the least complex sphere in the ball? The boundary, okay, right? Because they intersect at the origin, that's about as far away as you could get. Okay, right, so that's the least complex one. So now, Smale's theorem says this, that given sigma, there exists sigma t such that sigma 0 equals sigma, and sigma 1 is the minimum of the complexity. Okay, right? Everything could be made uncomplex, right? So now the question is, can you do this greedily, right? Could you do this in the greedy fashion, or do you have to make the complexity go up? Right? I mean, it would be so nice to sort of just like imagine, you know, pumping some gas into there and then like letting it evolve, you know, maybe magnifying the hypersurface itself so it doesn't get self-intersections. That would be so beautiful and wonderful. But the question is that true? So here's the question. So suppose I'm given the complexity. Okay, so here's the thing. So, I'm running out of space. So here's the problem. If I know the complexity of my original hypersurface, how big can the soup over T, the inf over families. Okay, so the families are ones that start at sigma and end on the boundary. Okay, and then I look at soup of the complexity of the hypersurface. Okay. And so now you might say, well, this isn't yet a sentence. Yet. Now it's a sentence. Okay. Right, I'm interested in trying to understand this quantity, and this really does make sense. There's some kind of not very hard pre-compactment theorem you could prove. Okay, this really, I mean, obviously, if I know the complexity, there are still going to be uncountably many hypersurfaces, but nevertheless, in some suitable topology, it's pre-compact. I don't want to talk about those issues. Okay, I mean, you really can, there does exist, it's a formality that you really can bound the worst C of sigma t in terms of C of sigma. This really is a finite quantity. Okay, you could have imagined that for each hypersurface, you get a different one, and that since it's an uncountable set, but we're topologists, we know that topology will govern something. Okay, so the theorem, here is a theorem of Nabokov. Great theorem for me to mention at this, because this is a theorem in his PhD thesis, so it's definitely good for a graduate student conference, is that it is not true that, okay, that sigma, oh, so what should I call this quantity? I'll call this, I'm going to screw you all. I'm going to call that capital C of sigma, right? What the hell? It's not true that this is like a tower of exponentials. Okay, where the number of twos is like C of sigma factorial, factorial, factorial. Okay, okay, right? Okay, that no kind of normal bound that any human being could see will work. Okay, okay, and what more precisely it means that if little c of sigma is sufficiently large, if you pick up some sufficiently large number, then there will always exist a hypersurface with that complexity that disproves this bound. Okay, that's a yet more refined theorem that he proved. Okay, this theorem just says that any such bound fails infinitely often, but actually it fails for all sufficiently large numbers, and so on. And this is kind of an amazing, I think this is a very amazing theorem. And I think that this was, so I think this is a theorem of the 1990s. I don't think I'm going to describe the proof very much because I've done it in courses. It's a little boring. Oh, I wrote a book about this kind of mathematics, what this is related to. Let me just give you a hint that the real truth is nobody in the world proves an estimate like that. Okay? Okay? Even a tower of exponentials is rarely ever proved. Okay? With a big tower, although sometimes it happens. But one like this, just face it, the real truth is that he proved something stronger than that, which is that it's not bounded by any recursive function. Okay? Not even a primitive recursive function. And once you begin hearing that, you realize that there has to be logic involved. Okay? And that is what the secret of this theorem is. But it's absolutely amazing, right? So firstly, let's just think about what the theorem says. The theorem says something always exists, right? If you gave me this hypersphere, this sphere inside, something or other exists, and you should be amazed at how complicated that thing is. Okay, so I mean, it really is an amazing theorem. Okay, what Alex's proof is based on is the fact that there is a secret logical hypothesis in the theorem. Does anyone see any logic in the theorem, in the hypothesis of the theorem? Okay, let's see. Well, if I know, well, I don't know, that's maybe philosophy or psychology. Okay, well, there's some secret here, right? In order to define this, I needed to know that sigma was a hypersphere. Okay? In order to define C of sigma, I never needed that. Right? What was the definition? The definition was you take the normals. Right? Normals are defined for hypersurfaces, not just hyperspheres. Okay? So what's secretly going on is that you're having a functional on some space, but the functional is defined on a much larger space. In this case, it's defined on the space of all hypersurfaces. Okay? And what ends up happening is that if you had a bound on this function, okay, then you would use it to build an algorithm that would tell you whether a hypersurface was actually the sphere or not. Okay? So really, if you had anything at all that was computable, no matter how bad the computation was, ultimately it would give rise to this. Okay? Now, if you want to think about, just to give you a hint about some of the things that this becomes related to, is you should therefore think, oh, here I have, I'm going to use, I love this, this is the toolbox. I'm going to use this high-tech tool. I shouldn't make fun. This is the kind of high-tech tools they had when I was a graduate student. Everywhere. So, okay, one way to think about it, by the way, is that here I have some kind of space of hypersurfaces. Okay? And here I have, this notion of complexity. That's a function from this space to the real line, right? The fact that it's a decent complexity notion means that that the sub-level sets have cut some kind of compactness properties. Otherwise, you wouldn't really want to call it a complexity. If there are infinitely many really different things in complexity 50, then it doesn't feel like a good complexity notion for a lot of purposes. But now what this is saying is that even though the space of hypersurfaces, thanks to Mr. Snell, is connected, right? What this is saying is that, oh, but if you look at the local minima, right, you might have to go very, very high, to say connect the local minimum to a global minimum, or therefore a local minimum to another local minimum, right? Right? If you could just lower which local minimum you're at in a reasonable way, then you would keep on doing it until you got it down to the globalist one, right? So what this ends up doing is it gives you some idea that there are problems in logic or theoretical computer science and things like that that sometimes give you more critical points for functionals than you should be entitled to just by, say, Morse inequalities or the usual things that topologists do. So anyway, so that's sort of one direction that comes out of thinking about quantitative problems. And now I'm going to dismiss Smale for the rest of this talk. And he's there lurking in the background in some of these ideas. So now we talk about problem number 2, which is René Tom's problem. Okay? So here's a theorem of Gromov. Oh, no, I need to give you a definition before I give you the theorem. Just like the last time, I have to tell you what the complexity of a manifold is. So the complexity of a manifold will be the nth of the volume of the manifold with all Riemannian metrics. Well, no, that's stupid because just multiply your metric by epsilon and you get it to have smaller volume. Okay, so Gromov wouldn't do that. I mean, I might do that for a month or two before someone points it out. Okay, so you better assume something about G. So what you do is you assume that the curvature of G, the sectional curvatures, are bounded above by 1. And in order to not have to think about collapse, we'll also assume that the injectivity radius of G is at least 1. Okay. So is this clear? So basically the idea is this. I look at a compact smooth manifold, okay? And I want to assume that I want to say that its complexity is the complexity of its least complicated metric. And so I'm not interested in really doing any kind of local mathematics. I'm being a topologist. I just want to think globally. So I'm going to assume a way that the local structure is pretty flat, and that all balls of size 1 are balls. Okay, right? So that therefore the complexity is basically how many nice simple coordinate charts does it take to cover the manifold. I mean, that's basically what this is. Okay, I mean, and you're right, and you're not allowing yourself geometrically complicated coordinate charts. Right? So it's a very, very simple notion of complexity, not bad. And now Gromov's question, I'll state his theorem, is that if M equals the boundary of W, then there exists a W. Okay, maybe I'll call it a W prime to not be confusing unnecessarily for once. Okay? This is my one concession to you guys. Okay? Don't squander it. But there exists such that the complexity of W prime is at most 2 to the 2 to the 2 to the 2 to the complexity of M, where the number of 2's is n minus 2. Okay? Okay? So this is better, by the way, right? That one was not a tower of exponentials. Okay? And this is a tower of exponentials. Okay? Right? So, there is a bound. Okay? But Mr. Gromov, bless his soul, did not believe that his result was the best possible. I'm going to call it a conjecture, although I don't know, I don't remember whether Gromov did or not. I think I heard conjecture this. But anyway, that's really that the complexity of W prime is really less than some constant depending on dimension times the complexity of that. Okay? Right? He proved a tower of exponentials, which, by the way, is pretty non-trivial, right? We've seen that these existential theorems in topology don't guarantee that you get a tower of exponentials. Okay? And here, you might imagine that there's some induction on dimension going on, and each dimension, that somehow dimensions 1 and 2 and 0, 0 is a dimension, remember, are all pretty easy. But you start doing your work when you get to 3 manifolds, and each time, you pay for a single exponential during the course of your induction. And that's not insanely off from Gromov's idea. But he believed that the truth was linear, or at least he said the truth was linear. I think that he was just laying down the gauntlet, to just show how far off what could be true from what is true. But anyway, and let's see, in order to, I should have said that if I have a manifold with boundary, I make a similar something. Maybe you assume that there's a collar of size 1 near the boundary or something. Again, the philosophy is we're not interested in doing any local work. All of our questions are essentially global. Okay? So this is, so Gromov, this is all goes back to like 90, let's say 96, 97, something like that. And I found this, really disturbing, this problem here. And it really comes to, it comes to show how non-explicit the methods of topology are. See, and one of the reasons why this was really an important problem is because the methods of René Thom, there's this whole philosophy of algebraicization that a lot of topology is based on. You start off with a geometric problem, you associate to it a function, then you do algebraic topology with the function, and then afterwards you reverse the process and you pull out something geometric. Okay? So let me start by reminding you how that goes in the René Thom theorem, because that is what this situation calls for. Okay, so let me first sketch Thom's theorem. Okay. And what I'll do, and okay. So here goes. I mean, Thom didn't actually call my steps are different than Thom's steps. But the ideas are all his. Although, he's dead now, so we won't complain about it. Sadly enough. Okay, so the first step is you take M and you embed it inside some very high-dimensional Euclidean space. Okay? You could set N for the purpose of this argument to be 2M plus 3. 2m plus 2 would work, but later on, well, who knows? Future is working. Okay, right, so I'm going to start off and I'm going to embed my manifold in the sphere, right? You know, remember, Tom wasn't interested in any kind of estimates on anything, so he just used the Whitney embedding theorem, right? You could stick it inside of the sphere, you know, that's something you can do, so you do it. Okay, now, step 2 is that from this embedding, assign a map from Sn. I'm going to write it out in English, and then I will unravel it on the next blackboard, so that it'll be mathematics, so you understand it better. The Tom space of the universal bundle over the Grassmannian of, I guess it's of M planes in Rn. Okay? So you could, by the way, Tom did not call this the Tom space. Okay? He didn't even call it T spaces, you know, following on. Okay. So let me just explain what this procedure is. Okay. This here is my sphere. Okay, it looks a lot like a Euclidean space. So over here I have a point at infinity. Okay? And over here I have my manifold M. Okay? And now here I have a little epsilon tubular neighborhood. Okay, and that's what a little neighborhood of the manifold looks like. So now I'm going to describe to you. Over here I have, this is my schematic. This is the Grassmannian of n minus n planes in Rn. Okay? So, firstly, this is the same thing as the Grassmannian of little n planes. Why? Because if you have a plane, it has an orthogonal complement. Okay, so these are exactly the same spaces. It's more convenient to deal with the normal bundle than the tangent bundle. Okay, so Tom does. Okay, so you'll notice how the hypothesis of the theorem is now a little different than the method of proof, but who cares? You know, that's not what got Tom to feel better. Okay, just about everything else. Now, over this Grassmannian, there's a canonical bundle where this point is a vector space, right? It's a vector subspace of Rn, okay? And it's of dimension n minus n, so that's what I put there. Okay? Now, if I have a point in this tubular neighborhood, okay, it corresponds to a particular point on the manifold, and at that manifold I have the normal direction at that manifold. Okay? I have an identification of this normal space is exactly, I guess I should draw more of the Grassmannian, it's exactly going to that point, and this point here really corresponds to some specific point in that vector space. Okay? So there's a map, so we have a map from the epsilon normal bundle of M to the epsilon tubular neighborhood, the epsilon, what should I call it? The epsilon disk bundle of the Grassmannian. Okay? So what we'll do is we'll take this thing and we'll multiply it by 1 over epsilon. Okay? And that way this thing here will be, so I take 1 over epsilon times the obvious map. Okay? So by 1 over epsilon, of course, in the Grassmannian direction it does nothing, but in the fiber direction it multiplies by that scalar. Okay? And what that does is all of these points here, okay, so this will map this and the epsilon sphere bundle of M to this, such that this goes to the unit sphere. Okay? So now here's what the Tom space is. I take the unit disk bundle over the Grassmannian. and identify the boundary is identified with the point of infinity. Okay, I'm just going to, okay? Right, so this is going to be, this is basically a manifold with one singular point. Right? This point at infinity is a pretty crappy point, usually. For the Grassmannian of lines, it's not a crappy point, but usually it's a pretty crappy point. But it's a nice smooth manifold anywhere else. The Grassmannian lives inside here. Okay, and now I could map everything out here, right? The whole sphere is being mapped to that point. So now I can map everything in the complement of this little neighborhood to that point. Okay? So what did I call this map a name? No, I didn't. So let me call this map here T sub m. Give Renee Tom some credit. Okay? So now that's how I've now built a map, T sub m. This will be a map from the sphere of dimension n to this space, which is called the Tom space of that Grassmannian, of the universal bundle over the Grassmannian. Right? I mean, this construction, of course, I could take for any vector bundle over a space. I could do this construction. I could look at the unit bundle. I could then shrink the boundary to a point. So that's called the Tom space of a bundle. You might have learned the Tom isomorphism theorem when you did algebraic topology. That was one of the theorems that Renee Tom did to analyze this space. Okay, he was interested, right? So now, what he's saying is, so T sub m is an element in pi n, right? It's a homotopy group of some Tom space. Now, by the Tom isomorphism theorem, H upper n of this Tom space is isomorphic to H n minus n of the Grassmannian. Okay? Right? And that's what the Tom isomorphism theorem was proven to do. It was to relate at least the homology of the space that you're interested in to a, and homology of Grassmannians, that's classical mathematics that was available to Tom. And his main, and then of course, so step end. Okay, there's obviously a step in between that I'm skipping, is to show that T sub m equals 0 if and only if T sub m of the fundamental class equals 0, right? T of the in equals 0 in the homology of the Grassmannian. Okay, I mean, I've abused notation. So this should be T sub m of the class of the sphere, right? But this will be the same thing as the tangent bundle associated to the tangent class in the homology of the Grassmannian. Right? This one here should be living in the homology of the Tom space. So anyway, so step n, this is called algebraic topology. And I don't want to insult it, but I don't want to talk about it either. Okay? Right, so you know the Hurewicz isomorphism theorem. Lots of times you study homotopy groups of things by studying homology, and you might know that usually it fails. Right, you need to have highly connected spaces and so on. Right, so computing homotopy is a hard job. Okay, and that's part of what the frustration behind Renee Tom's theorem is. Okay, okay. So far we haven't done anything. I haven't told you how to construct a null cobordism. Right, I just showed you that if I had a map, then if I had a manifold, I'd get myself now a map. And so the missing step, which I will put over here, is that T sub m is null homotopic if and only if there exists a W such that m is the boundary of W. Okay, so this is sort of a key geometric step. Okay, and let me sketch this because it's really easy. Okay, so the key thing to notice is that m is really T sub m inverse of the Grassmannian. Okay, and what I really mean is, this map from the sphere to this weirdo space, right? That weirdo space is a smooth manifold except for a point. So if you take the Grassmannian, that doesn't get anywhere near the point. So I could talk about what it means for the map to be transverse to the Grassmannian. And the way we built the map, it is transverse to the Grassmannian. And we know that that's what you do in differential topology. How do we know that? Because of René Thom's paper, by the way. He introduced transversality. He called it T-regularity, or something in French, actually. But, you know, with a lot of good work in that. But anyway, and now the point is, of course, if I had M being the boundary of W, so here I would be having the sphere. This is a picture of the sphere. This is now a picture of the sphere cross I. Here I have M, and then it bounds some W on the inside. Okay? Then I would have a T sub W defined by the same process, and it would map Sn cross 0, 1 to the Thom space. So if there were a W, I do the same construction, it gives me a null homotopy. Conversely, if I had a null homotopy, so over here, it's all mapping to the constant map, namely the point at infinity, and then I take the transverse inverse image of a submanifold, then that will be the null cobordism of W. Okay? Okay? So that is, okay, that wasn't bad. That was 15 minutes. That's a summary of René Thom's 1957, I don't remember, paper. Okay, very, very cool, but now it makes you realize this is pretty hard, right? If I have a smooth map and I want to understand, say, the inverse image of a point, and I want to know, well, how big is the homology, right? Any kind of measurement you want to take of that, you know, I mean, typically you use things like the inverse function theorem, right, to even know that it's smooth, and then if you want to understand its complexity, it's not so easy, right? And if you want to really understand the complexity of the inverse function theorem, pretty soon you're doing analysis, and that seems like a horrible price to pay. Okay, so anyway, so this is the struggle, right? This is the struggle. You've seen the proof, and there are all sorts of, you know, bad news. How in the world, if you start off with the manifold, so what René Thom theorem is that cobordism is isomorphic to a homotopy group, and then he computes the homotopy group. Doing that calculation involves lots of spectral sequences, lots of algebraic arguments. But how in the world can you, and when you do algebra, it really screws you up in trying to learn estimates. Because in algebra, you make a group, and when A is isomorphic to B, equivalent to B, you say they're equal. Which means you don't get to pay any royalties, right? So if I'm going to have some kind of, if I know that A is equal to B and B is equal to C, right? So I'm interested in this problem, I should have to pay the sum, right? Because I have a cobordism from A to B and then a cobordism from B to C. I'm going to take the union of those two, and the volumes will be adding. So I should have to pay every time I do it, but the algebraists insist on using that equal sign, okay? And that means that I get a free lunch, which is fine, except if I want to know how much the lunch costs. Right? I mean, here, right, we're specifically trying to understand the complexity of the objects, and that's what's thrown away in this kind of reduction to algebra. Okay. So, okay. So here is an intermediate step. Is another conjecture of Gromov. This one, I'm going to remove the J. And it's a con of Gromov. I mean, I don't think that Gromov ever really conjectured this. I mean, this was more speculation, even to Gromov's way of thinking. And it goes like this. I'll explain to you why it's relevant, why it's not enough, and then why it's false. Okay? But it's not so bad. Okay? And that's still, remember, in terms of the scope of the talk, we're still in the optimism side. So the conjecture of Gromov is this. It says, suppose you have X and Y finite complexes. Okay. Y simply connected. Then there exists some constant such that if F and G map X to Y are homotopic L Lipschitz maps. I won't remind you what homotopic means, but I will remind you what L Lipschitz means. Then F and G are homotopic through KL. So now let me express what this conjecture says and say why it has something to do with this problem, and then explain why it's not enough for this problem, and so on and so forth. Okay. So here's, remember the definition of Lipschitz. F is L Lipschitz if the distance between f of x and f of x prime is at most L times the distance between x and x. Okay? So if you're in a smooth world, right, this means that, you know, in the tangent direction, nothing is multiplied by more than L. Okay, right? So, and if you're, you know, and then this will tell you if you're mapping between compact things, a set of such maps is pre-compact. This is a complexity notion for functions. Okay, so this is a good thing. And now you can certainly imagine that there should be some issue if I have complexity notions for manifolds, right, and then I associate functions to manifolds, right? There should be a connection between the complexity function of the induced maps and the complexities of the original manifolds. Okay, so this suggests that non-complex manifolds should give rise to not so complex functions. Okay, right? That would be, you know, sort of the idea. Now, so then I would have this my manifold, and right, its geometry wasn't so complicated. I have to stick it in Euclidean space. Okay, so this begins talking about quantitative embedding theory, which there are countless conferences about things related to that. You know, like which Banach spaces do which finite graphs embed in and things like that. But now you need to do it for Riemannian manifolds instead. Okay, so then you would want get some information about the function. Now, if you believe this conjecture of Gromov, then the null homotopy would be through functions that are much more complicated. Okay? So, right? So that definitely sounds like it's progress. Right? Okay? And then you would want to take the transverse inverse image and you know, go home with a less complex null cobordism than Tom gave you, right? As a result of doing this. Okay? Right? That would be the idea. Okay? So that idea is a good idea and a bad idea. I mean, it's a good idea, but it's not enough. Okay? So, you see, here's it's not enough. What you really need, what you seem to need, given that we have to solve a problem, I can't say what you really need. Okay? What you seem to need is a KL Lipschitz homotopy between F and G. Okay, so what does that mean? So remember a homotopy, and I said I wasn't going to tell you what a homotopy is, but now I'm lying. Okay, that's a map from X cross 0, 1 to Y, right? Gromov's conjecture was about what's going on the individual slices, right? But if I wanted to, remember, I'm going to try to control the inverse image under the homotopy. So if the time, if I don't control the motion in the time direction, this will absolutely kill me. Okay? So, you know. Okay? So this is what you actually need to do, and this isn't automatic. So for people who like three-dimensional topology, I'll mention an example that I think I learned from Kevin White, is that there are null homotopic curves on Sol manifolds, okay, which they have length L, and they're, you know, and you can null homotop them all the way down to 0 without increasing L, but the length of the homotopy, okay, if you insist that the homotopy be Lipschitz, so then you could so if you like, the alternative would say, what would be the Lipschitz constant in the time direction that grows exponentially with L? Okay? And if you think about a higher dimensional domain, what you would be led to would be exponential in L to the dimension of x. So if one knew this con of Gromov, you would be able to get Gromov's conjecture not down to linear or even polynomial, but you would get an exponential of polynomial. That would be sort of what would go on, because it's not controlling the time direction. Okay? But it would definitely be progress. So I have 5 minutes left, which therefore means that I have to completely cheat. So I shall. Okay, so that's my 5-minute warning. So the first is the theorem of Chambers, Doppler, Manin, and mine from last year. And it says the following. It says that if the rational cohomology of Y is a polynomial, this is too awful, but let me just say, is the same as the rational cohomology of a product of odd dimensional spheres. Okay? So it's obvious that this is just a technical thing. Unfortunately, it's a technical thing that's necessary, but it's still a necessary thing. Then, for any x, there exists a case of x. Okay, it actually depends on it, such that L Lipschitz. Okay, so Y is simply connected. That went without saying, because that was part of Gromov's hypothesis. Said that if you have an L Lipschitz maps that are homotopic, then they are KXL Lipschitz homotopic. And it goes without saying that all of the Tom spaces of Grassmannians that occur in this problem have this hypothesis. Okay, I'm not going, okay? Okay, so it applies to it. So this would be good news, right? So this does what Gromov needs for the situation of this problem. What sort of, yeah, okay, I can't talk about the things I don't have time for, so I shall resist. And this fall, Fedya and I, okay, so in terms of what the original outcome, then we, this fall, Fedya and I, by combining this with some ideas of Gromov and Guth, we're able to show that this implies that if M, okay, let me say it this way, that for all epsilon, if Mn is a boundary, then there exists a W such that the complexity of W is less than some constant, depending on N and epsilon, the complexity of M to the 1 plus epsilon. Okay? So Gromov had hoped to make this linear, and we have it now for every power bigger than 1. Okay? I personally suspect there might be an inequality like C of M log C of M or something, just to screw around with us. I don't know that I conjecture that, but I actually think there. So let me just say that this theorem, with the idea, sort of using Rene Tom's ideas and just doing sort of straightforward-ish embedding theory, what that would end up giving you would be this. you'd get a polynomial estimate. In each dimension, there would be a polynomial estimate, but the degree of the polynomial would grow exponentially with dimension. Okay? This part uses being more careful with the embeddings. And sort of the thing that really surprised me in the course of doing this is that you're struggling against something in here. As you make the dimension of the sphere larger, okay, so then during the course of your null homotopy, there are bigger and bigger things that you're not controlling, right? So remember, the inverse image of the Grassmannian is a null cobordism, right? So if you're having, a big ball that has lots and lots of stuff in it, right, then there's sort of lots and lots of room for the inverse image of that Grassmannian. So the dimension of the, so you don't want the dimension of the sphere to grow too large, because that would be bad news. Okay? On the other hand, it turns out that if you make the dimension around Whitney embedding, you do it like 2n plus 1 or 2n plus 2, what that does is it turns out it forces strands of the manifold to get quite close to each other. Now, when the strands are very close to each other, that means that the epsilon is very small. That means that when you multiply that by that 1 over epsilon, you're going to increase the Lipschitz constant. So what you really have to do is pick some constant times the dimension to embed it in, and then you let the constant increase. As that constant increases, that turns out to improve this to 1 plus epsilon. But, so there's sort of various refined aspects to this. I don't have time to say any more.